Hey folks, today we have none other than Rishi from MongoDB. He's a senior solution engineer and architect, and he helps all his clients to get onboarded onto MongoDB and leverage it where feasible. You will notice a couple of times MongoDB has featured in the news in recent days for everything related to RAG and AI. They have recently acquired uh, quite a few intellectual properties which can help them with this journey. So now we'll hear from Rishi.
Hey, thank you so much for introducing me. Hey, everyone. Today, as you guys already know, that we have AI-driven applications, we have MongoDB, and how we take care of that in MongoDB, and that's the agenda for today. So, I'll be going a little traditional way, going through a presentation, which I get it if you find it boring, but I'll try to make it as interesting as possible for you guys. We'll be talking about few concepts throughout this session. And towards the end of it, I'll probably also be going through a live demo. So I think with any further ado, should I start sharing my screen, Amit? Is that okay?
Absolutely. So one thing to always remember that Rishi is going to show us everything to do with RAG, why RAG, when we should implement RAG, and I think it's something which everyone is very interested in today's AI-driven age.
Perfect. So let's see. Let's get this interesting. All right. All right. Can you please confirm once you can see my screen?
Yes, we can see a screen.
All right, perfect. All right, everybody, welcome. I hope you're having a good day wherever you are. Good morning, good evening. Uh, so today, what we are going to be talking about is vector search in MongoDB. As already Amit has introduced me, I work as a senior consulting engineer here at MongoDB. Day in day job is working with our customers from small small startups to big enterprises. I help them implement MongoDB in their bigger architecture. So one of the use cases that keeps coming up is we are all talking about AI. What how an enterprise or a company can actually use AI, right? So very recently, it's not recent anymore, but it's been a couple of years now. We have been working hard within MongoDB to get our vector search implementation work in favor of customers when they are trying to build their AI driven applications. So, as Amit already said, on today's agenda, we have few things that we'll be talking about. I'm going to go from the basics, start from scratch, give you an introduction about as simple as what a vector is, right? If you're from a mathematics background, you probably have an idea about it, but we'll still go over it real quick. So, to make this session more useful and informative, uh, I'll be going over a few topics like sparse and dense vectors, what they mean, uh, general search technology, what DFIDF stands for, how you can actually use that for scoring and making relevant searches boil up. We'll talk about that, what syntactic search means versus what semantic search means. Uh, all of the things that I'm going to be talking about are industry wide terms and knowledge. So it's not just specific to MongoDB. We are just helping you understand how that is done. And
This this is very interesting. What all you have covered in the agenda. I think there will be quite a few items for people who have not used RAG before, these are all new terms.
def-
People who are, sorry, go ahead.
sorry, go for it.
For people who have not used, like for me, when before you walked me through this before, I was not aware of this terminology and I had not used any of this. I have used MCP servers, I've heard of RAG, but it's very interesting to see all these background items which are required in the background while architecting your RAG setup.
Yeah, no, definitely. I mean, I think same as you. When I started off, I didn't know any of this. I knew some of it, but the depth in which we got to get exposure on those things is different, right? So over the period of time, what we have seen people lag in terms of the gap or the learning curve that is required. I've tried to cover as much as I could in that sense, right? Again, AI is a vast topic, so you could go on forever talking about things. But here I've tried to cover as much as I could to get the knowledge rolling.
This is exciting.
Cool. So then we'll be talking about how do you represent words in the higher dimensions, what higher dimensions mean to begin with, right? I'll be getting into that as well. What vector search architecture looks like. The reason before I'm building up all of these, before I get to RAG architecture, is because RAG architecture's basic starts from vector search. And then last but not the least, I'll be talking about the syntaxes of how you can do vector search in MongoDB, and then do a quick demo of how that is going to look like in MongoDB, and then cover the RAG architecture. With that, can I continue on to the next one?
Yes.
All right. So, so what are vectors? So, as I was saying, in mathematics, a vector is an object, a mathematical object that has both magnitude and a direction. If you see on the diagram on the right-hand side, you usually have XY axis. That's basics of drawing a vector, right? And it has a magnitude, u. U is the magnitude which says how long it is, or or how far it is from something, right? From the apex of the XY axis. So it's represented as a list of numbers. So if you have a 2D space, if it's XY axis, you probably write it as as 1 to whatever the point coordinate that you're trying to point out. So it's represented as an array of numbers. In computer science, you can represent it as an array of numbers. So these numbers, number of components of a vector depends on the dimensions in the vector space in which the vector resides. So if you have 3D, then it will have 3 numbers in the array. If you have 4D, it will have 4 numbers in the array, so on and so forth. Now, when I say these numbers are basically the dimensions, right? What 1D, 2D, 3D, 4D, 5D, and so on and so forth. The dimensions are basically the features. I'll help you understand what that means in a bit. But before we get there, let's try to understand what sparse vectors versus dense vector means, right? So in sparse vectors, most of these dimensions that are part of the array are 0, right? So if you look at the example here, you have 0, 1, 0, 0, 1, 0. That just means that there's a dimension present, and for the rest of it, there's no dimension present. Again, the reason I pointed out that dimension is feature, just keep that in your mind as you're thinking. It has some feature, it doesn't have some feature in terms of binary numbers, 0, 1.
Yeah. So one thing to ask in that example below, to clarify, there are 6 dimensions mentioned there. Is that correct?
1, 2, 3. No, there are 4, 5. Yeah, 6 dimensions. Yeah.
Yeah. Awesome. This is just to clarify for anyone who's watching. When that whole array is basically the number of digits in that array would be the dimension number as well.
Yes. So that's what sparse vector is. So basically, your sparse, as the word says, it has lesser information packed in it, right? Then comes dense vectors. Dense vectors are where you try to pack more information. So most of the numbers would be non-zero numbers. It could mean different things Negative number can mean lesser part of that dimension is present in that vector space, but positive could mean it has more part of uh, that particular dimension present in the array. So that dimension again is feature, more of that feature present in there. So it
Yeah.
stores more complex relationships and more information in sparse, in dense vectors. Sorry, go ahead.
So to just clarify, your dimensions, when you say it has those features, it's nothing but similarity to that dimension. So is it more similar to that dimension or less similar to that direct dimension?
Yes, exactly. Yeah. So it's as I say, dimension is a feature. Does certain word fall as in more closely to that feature, or does not fall close to that feature?
Yeah. Yeah, I'm just using similar etc. because there would be cases where people might not completely understand what feature means or dimension means. So it's
Same
definitely really
terminology.
helpful. Yeah,
It's the same thing. You can interchangeably use that wherever you want to.
awesome.
Yeah. So throughout the presentation, if I say a dimension or a feature, that's exactly the same thing.
Yeah,
So now let's try to understand the search technology itself, right? So TF-IDF, it stands for term frequency inverse document frequency. Too many words, right? So let's try to understand what that means. So term frequency is basically saying frequency of a word in a document. When I say a document, uh, it could be a single sentence. That's fine. So number of times a word has appeared in a sentence. Whereas inverse document frequency means rarity of a word in the corpus or a collection. So again, this is an industry word, industry used terminologies. You can Google it. TF-IDF uh, is a concept of scoring a sentence or relevance or a paragraph or any word generally.
yeah. So one question which people might have in this is how big can that document be? Is there any limit of that document? And in this case, is there any so term frequency would just be the frequency of that word in how big that document is. Is that correct?
Yes, so the document can be as big as you want it to be, but practically speaking, you wouldn't want it to be a very big document, right? Because you would generally want to, as they call chunking, the entire paragraph or group of sentences into smaller bits so that you can do more with smaller bit of information. But yeah, you can have it as big as you want. It really depends on your requirement. There are people I work with customers who have done an entire page. There are customers who have wanted to do any only paragraphs, which makes sense. But of course, it has to fall within that 16 MB limit of a document for MongoDB context, right? So MongoDB
Got
doesn't
it.
go beyond 16 MB in a single document, so it has to be
Hmm.
that. But you can make it as big as you want, and 16 MB is a big. So when we say document, it's a very big document, right?
Yeah,
It's like me writing a text file of 16 MB. That's a big
yeah,
document. So as I said, too many words. Let's try understand it through a formula. The formula is basically number of times a word X appears in a document divided by number of words present in a document, right? So if you have Amit works for Odyssey Cloud, that's like 4 or 5 words. So that is number of words in that document. And Amit is somebody we are searching for. So that is how many times Amit has appeared in that sentence. So that is what term frequency is. Whereas inverse document frequency is logarithm of number of documents in a corpus. When I say corpus, that's collection. And when I say collection, that's all the documents in a table. If you're coming from relational world, uh, tables are what we call them as collections in MongoDB. Database is still called database. Uh, and then number of documents where that X has appeared, right? So Amit could be having a lot of places where Amit is written in the set of documents in the entire collection. So the cross product of these two is what TF-IDF is. And that's how the scoring system works. Let's try to understand it with an example, if that is okay. So, say for example, I had a collection which had three sentences: orange is tasty, apple is tasty, pineapple is tasty. Again, for the sake of simplicity and to understand a concept, we have used very simple sentences here. So, now here, when you're trying to calculate the term frequency of, say, so now we're trying to do a scoring for one sentence, say, orange is tasty. So when you're trying to do a term frequency calculation, as you can see, orange has appeared. Number of times orange has appeared in that sentence is one, and number of total words in orange is tasty is three. So TF would be 1/3 if you go back to our formula that I was talking about. Number of times word orange has appeared in that entire sentence, and number of words that are present in that sentence itself. So similarly, is and tasty will have 1/3, 1/3 as well. So the IDF calculation will be number of uh, logarithm of number of documents in the collection divided by number of documents that contain that word. Right. So again, orange is tasty. Uh, for orange word, the IDF calculation would be log 3 by 1, which would be log 3. And is would be, it has appeared in three sentences three times. So it would be 3/3, and log of 1 is 0. And similarly for tasty, it would be 0. Now, this is a sparse collection, sparse vector, as you can see, right? It has more zeros than non-positive, than positive uh, numbers in there. So the TF-IDF score for orange is tasty would be cross product of TF and IDF for each and every word in there, right? So it would be 1/3 into log of 3, 1/3 into 0, 1/3 into 0, and both of them would be 0. So sparse, uh, the sparse number notation for it would look like 0.159, comma 0, comma 0. So this is how the scoring system works, and this is how you score each and every sentence. And when you do a regular search, you use that scoring system to bring the most relevant one up in the search. And it is similarly used in vector search as well. TF-IDF is a scoring system. This is a form of scoring system. So with that, let's try to switch gears and try to understand what syntactic search versus semantic search means. So syntactic search is syntactically similar sentences can have very different meanings. When I say that, so for example, the example I've mentioned there, Big Ben is in London, whereas London is in Big Ben. Now, Big Ben is in London is a more relevant uh, search that would be more correct, whereas London is in Big Ben is not correct, but and is not true either. But if you were to do a search for these two in a regular search system, both of them will get, based on our calculation, TF-IDF calculations that we were doing, both of them will get exactly same score. But that is not what our intention is. So that is what syntactic search does. It just looks for certain keywords and shows you all the relevant searches for those keywords. Whereas semantic search tries to look for meaning and context and relationship between the words when it is trying to uh, bring a search. Let's try to understand what that means in NLP. NLP is basically natural language processing. Most of us might have heard about it. It's a subfield of AI that focuses on enabling computers to understand and interpret human languages, right? So, semantic search is basically something that enables NLP is something that enables semantic search, right? Basically, you have these transformer models which generate certain things for you, which makes it easier for you to uh, get a relationship between the words. So we'll try to understand that more as we go throughout the presentation. but it heavily relies on technologies like deep learning, your machine learning, rule-based systems, right? Where you say certain thing is happening in a decision box, you go and put it here. If not, then go and put it there. Uh, so it has many real world applications, like you can do sentiment analysis. So say, for example, on Twitter, as an enterprise, you have a brand handle, and people are coming in and giving negative reviews about your brand or positive reviews about your brand, right? So sentiment analysis, where you can try to go through the entire review of a product or something and see whether the end user, the customer who you are catering to, is happy or not happy with your offering, right? And then
Yes.
chatbots, where you could be talking to a support, quote unquote, support rep, whereas where there's a knowledge hub, and this NLP is running in the background to get the data from that knowledge hub and reply to you, instead of somebody sitting there and searching through the knowledge hub to get information to you. Or speech recognition, image recognition, audio video recognition. So a lot of other applications NLP has. Sorry, Amit, did you have a question or should I move on?
No, no, move on.
So coming back to what we were talking about, sparse vectors, dense vectors. Now, dense vectors, as I said, stores more information, more complex data relationship between the data. Most dimensions are non-zero. As I said, attributes and features of a text are referred to as dimensions. It's basically, to make things easier, what we do is we do a numeric representation of this in higher vector space. So to help you understand, let's try to see this quick matrix chart here. Here, what we have done is these on the top are basically your dimensions, call them features, whatever you might want to say. And on the left hand side is your data. Now, here, to make it easy, we have put single words, but these could essentially be entire sentences. And then you take each and every word and then try to get more vector representation of that. Now, here, if you take a look at what features do we have: object, creature, male, female, gender, young, old, human, reptile, etc. Right? Now, when we are putting different animals in that category, we are saying cat, it cannot be an object. It is a creature. It's male, female. It can be male or female. So wherever you'll see that it's relevant to that word, you have put one. And wherever it's irrelevant, it's zero. Uh, Similarly for dog, table. And now, if you were having a new data to come in, like tiger, and you try to classify that, it will probably look similar to what cat says, because all of them are cat family, and most of the features would be same as cat. Now,
Mhm.
when it comes to actual discrete values that this vector assigns, we could have continuous numbers, continuous scale from -1 to 1, representing the probability that we can classify the word in a certain category. This allows us to capture finer details of a word or a sentence, right? So here, that's why. So this is more to help you understand what in binary sense it would mean. But in actuality, when we'll see it in the demo as well, when we generate the vector embeddings, it doesn't come off as 0, 1. It usually has this scale from -1 to 1.
So I do have a question for that. Now, if we have a sentence like a cat is fluffy,
Yeah.
on the left hand side is the words which you can have classification for, and the dimension values which are present. When do we get the dimension values? Is it already preset, all the dimension values?
No, so what you, so you'll see it, I'll talk about it in a bit, but what you actually do is you send the sentence through a transformer model. So there are two kind of models, right? We have language models, the LLMs, and then you have transformer models. Transformer models are based out of a concept where when you send a, it's not a black box if you understand it. If you send a sentence through that, What it essentially does is it takes each and every word and tries to find the nearest meaning to that, and gets all the nearest neighbors based on the vector magnitude that is for that particular word from that. I'll explain that in a bit. Maybe that will make it clearer. So again, dense vectors. So for example, you have orange is tasty, and you have orange has great service. Now, orange has is tasty. We are definitely talking about something that you can taste, right? So it's referring to a fruit. Now, the features that it can have is it can have colors, it can have weight. It probably wouldn't have a stock price, market cap, patent, earnings per share, weight, location. It wouldn't have those features. So in vector space notation, it could essentially look like 0.45, and these are all made up numbers, by the way, just FYI. So it could, and rest of the features that are not there, it just goes and puts in zero, or it could be a negative value, right?
Yeah.
So but Orange has great service. Orange is a telecom company in EMEA and probably other part of the world as well. So here we are referring to Orange as the telecom company Orange, which has probably color, it has a stock price, it probably has a market cap, patent, earnings per share. It probably doesn't have a weight because it's a
Hmm.
brand, and it probably has a location as well. So it will have those features. So this is how dense vectors are generated. If this makes a little more sense in that sense.
Yeah.
This is what I meant by features. Each and every dimension is a feature in itself. Which brings us to the almighty transformer-based models. So Hugging Face is an open source software company. We all probably have heard about them. I've kept it as a reference out there as well. They have a lot of transformer models, they have a lot of LLM models, a lot of open source models that are present. If you're curious, you can simply go to their website and it will show you all of the models that are being used today. They have different tabs on the top. You can go to models. The model that I'm going to be using for the demo today would be All-Mini L6 V2. It's freely available. You can use it as well. And these are pre-trained language models and are provided by Hugging Face, and you can it's community maintained and developed, and uh, there are a bunch of really good models available there. If you're curious, you can use that for your own personal projects as well. So let's get into the next part of the presentation, and probably soon we'll be done. So don't get too bored about it. We'll do a demo quickly after that. So, but it's important to understand what we are going to be doing in the demo, right? So approximate near algorithm, it's ANN algorithm. If you do a quick Google on it, you'll understand. It's called approximate nearest neighbor algorithm. Uh, so basically, imagine you have a set of data, a data set where you have dogs and cats, to keep it simple, right? You have dogs which have certain features, and that is classified into certain data set. You have a data set with cats, and that is classified into a different data set. Now imagine a point coming in, or a new data set coming in, and it is a tiger. Now when it is coming in, what it is going to do is it's going to see which are the closest features I match to. Now, if you have a cat family, it will probably be classified into that cat family dataset group, because that's where it will have most features. Now, that is where the nearest neighbor algorithm works, right? So, given a new data point, which in our case is tiger, it finds approximate closest points, the nearest neighbors in the training data set. Now, training data set is already made of dogs and cats, but it is going to go and find the nearest approximate closest points. So when I say approximate closest points, it's going to check for features that we were talking about just now. So if you set number equal to 3, what ANN will do is it will find 3 closest data points only. Now this is where number of dimensions come into play. So if you were interested in doing comparison for uh, more set of features, then this number would change from 3 to 1000 to 2000 to 10,000, how many ever you would want, right?
Mm-hmm.
Uh, so what ANN will do is ANN will find the three closest data points in the training data set. In our case, it would have found the cat family's three features and assign the new data point to that class most common among those three data points. This is what is called classification, right? A new data point comes
Got
in,
it.
classify it into the data sets. Now it's recommended to select an odd value for k, because there could be a case where a new data point comes and it finds exactly same number of features in two different data sets, and it gets wrongly classified into something else, right? So you would want this number to be always odd instead of uh, even numbers. So it's also called as lazy algorithm because it does not really build the model during the training, but it simply stores the training data set to keep predictions about new data points, right? New data point coming in, I'll go and classify it here, classify there. Now, when you're actually working on MongoDB, there's a concept of HNSW, hierarchical navigable small words. What it does is HNSW builds a hierarchical structure that allows for efficient nearest neighbor search. So basically, the lowest layer will have most uh, high number of neighbors that it has to search for. And as the layers keep going up, it brings the vectors down and makes the search quicker. What that essentially means is what Atlas Vector Search uses is the HNSW algorithm to do the indexing. So you'll see I'll create a vector search index as well. The index internally uses this algorithm to do or construct your vectors nearest neighbors based on this algorithm. If you're curious, you can do a quick HNSW Google and it will give you details on that. But that is what keeps the searches fast as well. You wouldn't want your vector search to run slow. Like you have
Yeah.
indexes for general queries in any database, those are to keep the things fast. And that's why vector search index is different. It just uses a different sort of algorithm to do that comparison when it is doing that ANN algorithm comparison to get the nearest points.
Yeah.
So we support this. So now, when you're doing this comparison, you have to find the distance between the data points, right? So we support different kind of distance metrics. There are a lot more,
Mm-hmm.
but we support Euclidean, cosine, dot product. I'll quickly go over each. Euclidean is basically as simple as scalar distance between the two data points, whereas cosine similarity is the angle of the distance between the two, and dot product is basically saying the angle multiplied by the magnitude between the two as well. So each have different use cases as well. uh, you can again Google it, you'll find what are the use cases for different kind of distance metrics. So again, what is vector search? Vector search is a type of search technology that uses mathematical representation of text data and queries. And dimensions of a vector are numerical representation of the features of an entity that we have been talking about so far. And it allows for more sophisticated search compared to simple syntactic search, the keyword based search versus context search. We store a list of points that make up a representation of a word or term in multidimensional space, then compare them how close other points or words or terms are to calculate the similarity between the words and the sentences, and then give you the most relevant search. Why is vector search needed? We have already seen that we need it for recommendation systems, sentiment analysis, text classification. There are a lot of real world applications you wouldn't want to use keyword based searches for. Quick look at the vector search architecture here. This is important. So you give it a data set of data. It runs it through the NLP model, which is our Hugging Face model that we'll be using for our demo, which is all mini LM L6V2, a mouthful of the model name. It generates some vector embeddings, and you go ahead and store them in MongoDB. Now, on the other side, what you do is you send your actual search query that I'm searching for this particular sentence or something. The only condition here is that when you do that query string search, it has to go through exactly same model in which you stored your data in, because the number of dimensions have to match when you're doing the comparison of searches between the query that is coming in versus the vectors that are already stored in the DB, which obviously says that MongoDB is also a vector store. It can store vector information as well. So when your query comes in, it goes through the exact same model, and that same query is represented in the form of list of numbers, and then it goes in to that index which has been created on the data in that HNSW form and does the search for us and retrieves the result and sends that out. So as I said, data goes through the ML model and embeddings are generated and stored in the vector store DB, which in our case is MongoDB. Quick vector search example: when you create an index, you are basically saying what field I want to be talking about when I'm looking for the vector embeddings, how many dimensions it's going to store, and what kind of similarity we'll be using. And type is just for us to understand that we are doing a vector search specific work. And your query is, if you're familiar with MongoDB, there are aggregation pipelines in which there's one of the pipeline is vector search, where you have to tell it what index to use. And then you have to tell it the query vector, which is basically your query that is coming in, that I'm searching for something, and what path the embedding is on, the same one that you used for creating the index. And then you have to say it the number of candidates that it has to look while it is doing that, right? It is different from how many dimensions you're storing. It's basically saying when this new data point is coming, how many nearest neighbors does it need to look for before it can classify that into a certain data set. And
So is
then
this going to be predefined, the number of candidates for everything, or every time there's a query that will change?
this can change. This can keep changing. Number of candidates can keep changing. How many ever you want to do the comparison against. We'll see it in a demo real quick, right?
Mm-hmm.
So with that, let me quickly get into the demo. So if there are people who are not familiar with MongoDB, this is your cluster. So I'll go back to my cluster. This is our cluster, which is a set of nodes. Uh, if you see, if I do a browse collection right now, we have some system DBs in there. What we won't have is any other database, right? So these are all system DBs, admin config and local DBs. So let's try to run a quick code. So here I've written few scripts in Python. If you see, we have the sentence transformers. Make sure you have two things, packages installed: sentence transformers and PyMongo library to connect to Mongo uh, MongoDB. It's a Python driver that you can install. Very simple, pip install. So what I'm going to do first is I'm going to generate vector embeddings, which will basically take these documents, which are 5 sentences, and generate the embeddings, the dimensions that we were talking about. It's going to generate 384 dimensions because I'm using the transformer model, which only generates 384 dimensions of dense vector space. So let's quickly run this code and see what happens. So here, ideally, what it should be doing in the background is it should be generating those 384 dimensions for each and every sentence. and pushing that into the DB. So the code is very simple. I've just used a sentence transformer model, all many LM L6v2. I gave it the number of documents. What I'm doing is I'm using that same sentence transformer uh, to encode each and every document into the 384 dimensions and just do an insert in a DB. Okay. So ideally, on our MongoDB side, if I do a quick refresh here, you would see that the vector tests is the DB that has been created, inside which we have a collection named vectors demo. And all those 5 sentences that we just pushed into the DB have been pushed along with an extra parameter as vector embeddings, which has 384 uh, dimensions, and it has been stored as an array. MongoDB gives you flexibility to have an array data type, which is a massive add-on in a NoSQL world, and we go in and store all of our dimensions. Now you'll see that there are no zeros or ones here. These are from -1 to +1. So whatever is closest, you keep putting it as dense as possible, and that's exactly what it will say here as well. Uh, that these are the 384 dimension dense vector spaces that
Yeah.
gets.
So this also translates to you can use any model that you want, either denser or sparser, based on your requirements.
Yes, you can make it 384 to 500 or 1000 or 2000, how much ever you want. There's a limit to number of these though that you can add, which we are trying to keep expanding as we keep growing. So I think today it's 8400. It was at some point, I know, half of that. uh,
Yeah.
so you can keep.
So sorry, go ahead.
So you can keep changing that based on the model that you're using. Sorry, go ahead.
Mhm. What is the most used model, generally speaking, by companies or people for internal, like, because we are talking about real world use cases. So we want to know what would ideally be the right model that people should use.
I wish I had an answer for that. The problem with that is nobody will have a perfect model that they can use, right? Because every industry has different requirements. So
Mhm.
manufacturing will have a different model, telecom will have a different model, retail will have a different model, pharmaceutical will have a different model. Uh, there are a lot of people who are using open source models. There are a lot of people who have had their own hosted LLM models as well, right? So they use
Yeah.
self-hosted LLM models. So there's no specific ideal model. All of these, even if you go in models and you do a quick, I don't know, telecom, for example, there would be hundreds of different telecom specific models that will come up here. So,
Yeah.
so the answer to that is depending on your requirement, it can have one model or another.
Mhm.
All right. So what we have done is we have generated vectors, pushed them into the DB. That's it, right? Nothing else. Now, to actually make the semantic search work for you, what you would want to do is first thing, I've kept some queries on the side so that I don't have to type them while we are on the call. So what I'll do is I'll create a search index, a vector search index here. Okay. So we have this nice cool feature where you can select search and vector search. And here you can create your search indexes or vector search indexes. What I'm going to do is I'm going to use a JSON editor, but you also have a visual editor option if you are interested in that. So I'll go in. It will automatically fill in the details that it wants to, but for our sake, we have some predefined queries that we have saved. So I'll use that. If you see, I'm using similarity as Euclidean here, the one that I was showing, cross product and cosine similarity, and path is vector embeddings. So all my embeddings are stored in this attribute, and then number of dimensions and type is just for us to understand. And this is going to be using HNSW in the background, the algorithm to do the searches fast. If you're curious, there are more options available which you can tweak in terms of quantization or in terms of your HNSW options as well. Not getting into those because, as I said, we have just 1 hour session here. All right, so I'll go ahead and create this search index. It takes some time for it to create that. So while it is doing that, what we'll do is we'll take a look at the semantic search code, right? So now comes the beautiful part of doing vector search, right? So what here we are going to do, as I was explaining in the architecture earlier, this is your query string, right? Where you're saying I'm going to be searching for something. It has to go through exact same model. So what we did earlier was we went through this model and generated embeddings for each and every sentence. Now, when the query string is coming, it needs to go through exactly same model. And then we'll be doing the comparison between those vectors. So that is what the code is going to do. Our index is ready at this point for 5 sentences. Now this is going to be an interesting part. So remember your sentences, okay? So we are doing football is a fun game. Football is called different things in different countries. Life is good. Professors put in a lot of effort, and technology has evolved a lot over the years. And then a small paragraph on Big Ben. In our semantic search, what I'm saying is, if you look at it, first we have just used the same model, and I'm taking a query, which is basically sample search queries that we are going to be putting in here. I'm saying generate the exact same, using the same model, generate the embeddings for it. Now I want to use that embedding as part of the query vector, do the comparison between these different terms. You can see my code, right?
Yes.
Okay.
No, right now we can see search and vector search.
Okay. I don't know why that happened, but
You will have to reshare potentially.
probably let me reshare it. I don't know. Are you seeing the code right now?
Now I can just see your browser with StreamYard.
Oh, sorry. Okay. Can you see it now?
We will find out. Yep, we can see your code.
All right, perfect. Sorry about that. So here, what we are saying is we'll be generating the embeddings for that sentence that is coming in form of queries, and we'll be putting that as a comparison in the search stages, right? So here, I'm searching for playing soccer feels good. We have nothing like that in the DB. What we have in the DB uh, is the 3 sentences, is the 5 sentences that we have stored already. I don't know why the screen share doesn't show you the DB now. I don't know if moving the.
Yeah, instead of selecting window, you might have to select entire screen, and then it would do
Okay,
the
okay.
entire screen.
Sorry, maybe that might be the case here.
Yeah, so then you can flip between windows, and we should still be able to see it.
Are you able to see it now? Okay, perfect.
Yes.
Okay, sorry about that. So here in semantic search, what I'm doing is I'm searching for playing soccer feels good, whereas here in DB we don't have anything like that stored. We have something closer to that, which is football is a fun game. So now, if I were to run this code, which is basically doing a search against that data, uh, using the vector search stage, it should ideally return us the football is a fun game, right? So let's see what it does. So it did return football is a fun game back to us. Even though what we've searched for is the playing soccer feels good. We
Yeah.
created the settings for vector query and we sent that as a parameter to vector search stage here. This is the part that I was talking about earlier. This number of candidates can be changed to whatever you want based on
Yeah.
uh, how many close points you want to be comparing against. And similarly, for other sentences as well, uh, just to prove the point, if I say the tower close to Parliament has a lot of history. So Big Ben is the tower that I'm talking about, and it's close to the Westminster Abbey where the Parliament sits. So if I run this script again, ideally it should give me something close to Big Ben, right? Because that
Mm-hmm.
has higher score. If you see, it gave me that sentence where I had Big Ben and Westminster clock tower and things like that, right? Well, although
Yeah.
in the actual sentence I never said it what I'm looking for. I just said the tower close to Parliament has a lot of
Yeah.
history. It went ahead and searched that for us.
Yeah. So one thing which I do want to do is translate this into more real world applications, right? So when you create a RAG database, as you showed us now, you have a database in MongoDB,
Yeah,
which are filled with collections. That would instead be with your documents, maybe your Confluence pages, maybe your SharePoint pages, and you would store that within MongoDB. Once you do that, you would define how many dimensions you want to search on and what is your limits, etc. You would then connect your respective model, whether it is OpenAI, Copilot, uh, you take your pick, Hugging Face. You would then connect that to your respective RAG database. And whenever you type in your queries, that would basically go first to the model, then to your RAG database. And if it finds any context within the RAG database, it would retrieve those respective solutions, answers, pages, depends on what you're fed into it.
right. Correct. So I think this is the part that I was holding on to the end is the actual sample RAG app architecture, right? So as you rightly said, right? So on the left hand side, so if you're an enterprise, a bank, or could be a retail system or anything else, right? You probably have a proprietary information, right? So generally, the term RAG, retrieval augmented generation, is used to remove hallucinations. When I say hallucinations, is these LLM models are trained up to a certain date. It all has a date. Anything beyond that has to be fine tuned into it. There are different ways to do it, and more expensive and more time consuming ways to do it. RAG helps you remove that extra work of hallucination. But you cannot implement RAG, or you're better off implementing RAG through a vector store. So, in this example, in this architecture, what we are doing is we are taking some of the proprietary information of an enterprise, private data. Now, imagine a situation. I think this is something that Amit, you and I were talking about when we were talking about the topics. Uh, Pluto was a planet before 2006, and the poor guy was decommissioned as planet after 2006. Uh, uh,
Legacy planet.
so, so imagine if you had an LLM model that was trained up to data on 2006 on planets, and you're in 2025 searching for the same answer, saying was Pluto a planet, it probably will still say it's a planet, but the poor guy isn't planet anymore. So uh, in those cases, that is a proprietary, quote unquote, proprietary information or private information that you can feed, stating that I have this new document where Pluto is not a planet anymore. Take that, do a text splitting, which is basically called chunking. Again, industry-wide term. You do not store the entire document as is in a single document. You chunk it into smaller pieces. Now, chunking can be done in different ways: words, sentences, or paragraphs, or pages. Uh, so, based on your need, you do this splitting, you run that through an embedding model and generate the same embeddings how we were generating earlier for our data, and you store that into a vector store, which in our case would be MongoDB. Now, if you have a question coming in, how you make it easier is you have language models which are trained to give it more human like responses and construct it in a different way. But if you run it through the embedding model, which was our vector search architecture, you do this first and get the contextual information out. What you can do is you can combine that contextual information along with the question that the end user has asked and send it into the language model, and language model will make it okay. I have this extra context, I'll remove that hallucination from the response where I have been trained till 2006 data, and I think Pluto is still a planet. I'll remove that based on your already information that you have stored in the vector store, and I'll give you the answer based on that, and it will give you the correct answer based on that. So this is one of the example RAG architectures. There are different RAG app
Got
architectures
it.
that are present there. This is one of the examples that I'm talking about. It's to remove
Mhm.
hallucination. You could do other things as well.
So one of the real world examples, and correct me if I'm wrong, is more like if you had a software application within your company, the architecture changes over time. And if you don't have context of the architecture changing over time, you might get incorrect information or inappropriate information.
Mhm.
Um, in such a use case, it would be handy to have something like a RAG model, which is constantly rebuilt as your architecture is progressing, so that you get the latest information.
Could be, yes. It could be one of the use cases where you can be using that as well.
Yeah. The other question people would generally have is, when should I use RAG and when should I use MCP? Because that is one of the most widely used things, right? Like there are two options. You go down RAG approach and you go down MCP approach. So I think that would be a primary question which people would also have.
Yeah, no, definitely. I think so. MongoDB has an MCP server as well, right? So you can use a MongoDB MCP server. MCP servers are different than RAG in the sense that when you're using an MCP server, you're interacting. It's more for agentic AI use cases, right? Where you have you're interacting with 10 different tools. So how MongoDB does it is, to give you an example, is you have all these client side Claude, Anthropic data models, you have OpenAI data models. What MongoDB MCP server does is you ask, how can I find all the collections in my database, right? What it will do is it will go get it information from the MongoDB tools and give you the exact query that you can write, because it's all these MCP servers are more for you, for your proprietary information, right? You install it on a server somewhere on your side, and then you use these MCP servers to go get the information. So that is what the more use case for MCP is. RAG is on a different side, hallucination removing or enhancing your current LLM models and build on top of that, if that makes sense.
Got it. So if I'm trying to build agentic workflows, I would
Yeah.
mostly use MCP servers.
Yes.
RAG is still useful even in agentic workflows to get appropriate information while updating this. So for example, if I'm updating a Jira ticket, the updation of the Jira ticket I can do using an Atlassian MCP server, but the information I put into the Jira ticket, that information can probably come from a RAG database, which will have the latest information. and ensures that the comment I add in or the certain additional information I add into the description is appropriate and latest.
100%. Yes.
Awesome.
I know we are at the hour. Just wanted to make sure we are conscious of time.
Absolutely. It's so for me, it's better to not stick to time and actually cover the concept than to try and stick to time and just cut it short.
No, perfect. So whatever works for you. I didn't want to eat up on the time. Just wanted to make sure.
Don't worry at all. We will definitely try and chunk this down later on and convert it into shorts so that people can actually translate this into smaller bite-sized information in case it's too overwhelming for them.
Sounds good.
Yeah. And this has been a fantastic session, Rishi. Really loved you walking us through the entire RAG concepts, all the background concepts which come before RAG. Before you need to know RAG, you need to understand vector search. You need to understand all the different concepts of sparse vector search, dense vector search. It was very, very informative and love that session. Hope to have you again on the session. And maybe next time we can talk about tutorials for people where people can get hands-on experience of implementing some of these things.
Yeah, no, 100% glad to be here. Thank you for having me here. And yeah, I'm more than happy to do more sessions whenever possible.
Thanks, everyone, and hope to see you all on our next session.
Thank you.